Thanks again for joining us for real-time data processing using AWS Lambda. At this time, I'd like to turn the floor over to your presenter, Tara Walker, AWS Technical Evangelist. Tara, you now have the floor.
Thank you so much. Welcome everyone, and I really appreciate you guys joining for real-time data processing using AWS Lambda. As she noted, I'm Tara Walker. I am a technical evangelist, and that's just a glorified way of saying a software engineer who actually likes to talk to people. Let's go ahead and get started today. What we'll be talking about is, again, obviously this real-time data processing, but we're specifically going to talk about the services that enable real-time data processing. The two main services that allow us to do this effectively are AWS Lambda with Amazon Kinesis. After we discuss those services, what we then will discuss is the architecture and the workflow leveraging those services for streaming data processing. Once we discuss that architecture, we're going to get into a demo that shows this architecture live and running. And then afterwards, we'll talk about some best practices that you can use as you're leveraging these two services to build your own data processing solutions. With that, let's get into the services for real-time data processing. First, let's discuss AWS Lambda. AWS Lambda is really a function in a code that allows for stateless execution triggered by events. To elaborate a little bit more, you can trigger invocations through direct API calls, sync or async. You can also use various service integrations like S3 or any event such as that when an entry is created and updated. You can use SNS or third-party triggers. You can additionally, like we're doing in this streaming example, have event sources like Kinesis or DynamoDB streams to make it easy to perform real-time data-driven auditing, analysis, and even notifications with Lambda. If you add the help of our Service API Gateway, you can create HTTP endpoints powered by these Lambda functions with a set of back-end microservices that then perform at scale. So AWS Lambda is a great tool for triggering code in the cloud that functions based upon events, so event-driven code. And again, this is serverless and stateless. A key word I'll say here again is stateless. Make sure you remember that your code should run as you develop it in a stateless manner. When I say your code can run in a stateless manner, obviously this services compute needs to have a language or support for some languages. Lambda supports Node.js, Java, and the Python languages. Because this is powered with AWS, we want to make sure that you're coding things the way you would like to code. So if you want to use other third-party services or libraries, we allow you to zip up those folders, those libraries, or any type of execution points that you need for your code and then give it to Lambda in a zip file. So that in turn enables other native supportive languages that you want to use. What's great about this serverless compute in the cloud with Lambda is you can do all of this without managing infrastructure, like managing EC2 instances or auto-scaling the groups of EC2 instances based upon the amount of bandwidth or scale or sheer demand that you need. All you have to do is give us your code and Lambda will handle the rest. Lambda is very easy to author. You can deploy it very simply, again, just giving a code, and it's easy to maintain. You can debug using CloudWatch logs. We'll show and talk about that later. And what this allows you to do, and this I think is the power of Lambda, is allows you to focus on your solution, your business logic, your purpose for creating and leveraging the service in the first place. This simply makes it easy for you to build these back-end services that perform and scale that are integral to it, creating your solution. A great marriage. When we talk about some of the benefits for Lambda, specifically when we're building a serverless data processing engine, productivity stands in mind. We want you to be productive in building your dynamic applications that allow for these massive pipe loads of data streaming through this processing engine. So of course I talked about there's no infrastructure to manage, But the thing you want to think about when you think about productivity, especially for streamless data processing with these boatloads of data and streaming data coming across, is performance at any scale. You want to ensure that whether you're getting data processing or streams coming in of data, whether they be 100 or 10,000 or even, let's say, 1,000,000, that it can scale and perform appropriately no matter what the amount of data coming across. Now, with that, you want to make sure that this is a cost-effective solution as well as efficiency. And Lambda, as the benefit of using this as a serverless data processing engine, gives you both of those things. It's cost-effective and it's efficient. Adding that with performance at any scale, Lambda becomes a great serverless option to build your data processing engine. And of course, as I noted, all you have to do is bring your own code. Run your code in the choice of your language, give it to Lambda, and you're raring to go. Last thing I'll say about this great benefit is you never pay for idle. When you create your own solutions here, typically what you have to do is keep a server open or polling or waiting, for lack of a better term, for your service to run or someone to request your service. With Lambda, you never pay for idle. Lambda only executes when triggered. So thinking about Lambda, it handles capacity, scaling, deployment, monitoring, logging, a web service front end, and security patching. This is all without waiting for something to trigger all of these things. It only triggers when the event that you deem that Lambda needs to execute on focuses the execution, runs, and you never pay for idle. All right, now that we talked about the benefits of Lambda, let's get to the other service that's integral to data processing ingestion with a streaming data solution. Let me introduce Amazon Kinesis. If you're not familiar with Kinesis, there are 3 main features or services as a part of the Kinesis offering. The first one is Amazon Kinesis Streams. You build your own custom applications that allow Kinesis to take that streaming data and process it or analyze it. So streams of data, that's Amazon Kinesis Streams. There also is Amazon Kinesis Firehose. It allows you to load massive amounts of streaming data into S3, which is our object storage, or Redshift, which is our data warehouse. And then we additionally have Amazon Kinesis Analytics. So you could easily take all of those data streams that you're gathering and perform standard SQL queries against them to analyze those data streams for points of data that's of interest to you. Remembering that this is a fully managed service that will allow you to scale in the cloud and support incoming data traffic, and storing that up to 24 hours as a default. You can synchronously then allow this with all this data to replicate across data centers. So you can support massive amounts of data replicated across data centers and support replayable retrievals of that data for 24 hours within seconds of just issuing a simple put function. With Amazon Kinesis libraries, sometimes you'll see this noted as Amazon KCL, you can build Amazon Kinesis applications yourself. Now, you also can build Amazon Kinesis applications using things other than the KCL, of course. You can leverage our SDKs. I'll show an example of that in the demo. But with Amazon Kinesis library, it's specifically designed to build Kinesis type of processing consumer applications. You can feed these applications using KCL into machine learning algorithms and then emitting this to services like either machine learning or EMR, for example. When we talk about streaming done the Amazon way or the AWS way, let's think of some key things that Kinesis provides for you. And right now I'm going to specifically talk about streams because, again, I'm going to leverage streams in this solution. To build a stream, it's extremely easy to provision and manage. Most people say, okay, that word easy is overused. But when I show you how quickly I can build this stream, I think you will agree with me. You can actually monitor and view that this actually has real-time latency. So you can collect at a real-time basis data streams and promptly respond to key business events and operational triggers. That's a key metric that you should know when examining and leveraging Kinesis as a service. This is done in real time. Another key that you should note, extremely flexible. You choose the service or the combination of services for your specific data streaming use case. And with Kinesis and Lambda, these services allow you the flexibility to either push your data to different services, push your data to custom applications, really address any use case that's specific to your needs. Now that I talked about some of the great benefits of Kinesis for streaming ingestion and continuous processing, so I talked about it's highly scalable, you can replay the reads, and durable. The second half of the power of Kinesis I didn't even get a chance to talk about. Let's talk about that now. What about continuous processing? Now, with continuous processing, one of the benefits and power of Lambda is that you can scale the amount of data you have based upon the shards you have. Think about shards as a huge bucket of memory allocation or data allocation where I can just dump as many records as I desire into. You have limits about how many records per shard can get there, but you can scale to as many shards as you desire. So what I can do, therefore, is I can iterate through these shards, and as I iterate through these shards, I can get the records, which has each record, and process it in an ordered manner. The data is replicated synchronously across AWS AZ, so you have resiliency and durability. And multiple applications can process from one stream concurrently in order of different rates. And that's the great thing. I can have this one stream that I can have Lambda process one thing for, have another application process another service for another use case. So remember, multiple applications can process data from one stream concurrently. And the data is available to be processed within seconds of a put record, that's the function that you use, being issued. Processing constructs include checkpointing and shard iteration. So with this continuous processing, I can checkpoint, I can replay the data, it allows for multiple concurrency, I can have multiple shards to increase the number of records and also increase the concurrency of the puts being done. And all of this allows for this processing to go to another application using KCL. You can use the other feature of Kinesis called Firehose to dump this data into a warehouse. I can use Kinesis Analytics. And then, of course, there's also Amazon AWS Lambda, which we're going to show. So you have a managed service with very low latency and an enabled data movement to any stores, engines, or applications that you desire. Now that we've talked about the two services that are core to making this whole data processing engine work, let's talk about the architecture for this actual data processing streaming. When we talk about the architecture, now that we know the services that are available for it, we need to talk about how those services integrate and how they work together. So the first thing you should know about the integration of these services is that it's going to use what we call a stream-based model, a pull model. Lambda is going to pull the records and the batches for available records from Kinesis. Now these batches are going to be passed to Lambda, and Lambda is going to invoke its function with those batches, those records of data, as its parameters. And then Kinesis, to make this happen, when you create your function, Kinesis will be mapped as an event source in Lambda. I'll actually show this live when we do the demo. What you also should know is that Lambda is invoked when it comes to invoking with Kinesis as a synchronous request response type. Now remember, Lambda can be invoked synchronously by Kinesis, but you can have different shards invoking Lambda synchronously. So if I have 5 shards, each of those shards can act independently and therefore invoke Lambda 5 times. We'll get into this in the best practices. Each Lambda function, or the Lambda function that's associated with this Kinesis stream, will be executed at least once. And I talked about the different shards, but remember, each of those shards will block in order of synchronous invocation. We'll talk about what that means later, but remember, Lambda function will invoke per shard, so you can have multiple Lambdas running concurrently based upon the shards. It's going to do synchronously, it's going to be executed at least once, and it's going to be in order of synchronous invocation. The event structure, when you talk about Lambda and Kinesis integration, the event received by Lambda is a collection of records from the Kinesis stream. Now I'll show this, but I'll mention it here. That event with those collection of records are received in a binary fashion. That's how we can get that huge throughput through the Lambda. What you would do then is decode that Base64 data that comes across the Lambda, and then you can leverage that for getting your records and manipulating and processing. You as the customer determines the max batch size, not the effective batch size. Now we'll talk about what the differences of those are, so don't worry, but you get to decide what your max batch size that Lambda will pull will be. But that necessarily is not the effective batch size. And again, we'll go into the best practices of what truly that means as you truly start to architect this using best practices. So let's look at the workflow of how this works in this architecture. I first have data input coming in, and this can come from multiple sources. It can come from an application, financial data like you're pulling data from the NASDAQ. We know lots of data flows through that very quickly. You can get server health metrics, so I want to know how well my server is doing. IoT data, I can have millions of IoT devices writing data to Kinesis. How about transaction orders? If I'm a company, let's say like Amazon, that's taking millions of orders a day for different products. All of those things and all of that data can then be funneled into Kinesis, which captures that data as a stream or captures that stream of data. Then, as an action, you can then either audit, condense, process, you can monitor, you can do various things with the stream. In order to do those actions of the monitoring, the processing, the storing, that's when Lambda comes in. It actually can work as your processing engine to process the stream. Then I could send that data, so the output of that data after I've analyzed and processed or even stored the data, to various places. If I want to store the data as my action, that may go to Redshift or S3. If I process that stream and I want to send a notification to someone that it's been processed, or maybe there's some abnormalities with the data, I can do that through SNS with an email or a push notification. If I want to have that stream be queued or either stored or a server that's waiting to do something with the data or running a website, I can send it to XQS, or for a queue, I can send it to SQS, and EC2. I can also have this process go to a custom application or a backend endpoint. Now, we talked about the flow. You saw how the data flows through from Kinesis to Lambda. Let's talk about what that common architecture is for real-time data processing with those two. So we'll do it in simple 1, 2, 3, 4 steps. Real-time data or event data is sent to Kinesis. You saw that earlier. And then what happens then is it allows me to invoke, based upon Kinesis being an event source, multiple functions to process that same event data. So you see here in my graph, I have Kinesis executing, and I have 2 Lambda functions that's processing those data. In step 2, if you look, Lambda function 1 is going to process that data and aggregate that data from that stream, but then it's going to store that data result into DynamoDB. This is very similar to what you'll see in our demo. Function 1 also sends those values to CloudWatch for simple monitoring of those metrics. Again, very similar to what you'll see in the demo, because actually in our demo, we're going to store the streaming data from DynamoDB, and we're also going to store the data that comes across into CloudWatch. Now note here that CloudWatch will store data about Lambda's invocation naturally, but I can also send specific data that I want to make sure gets shown with my Lambda invocation to CloudWatch as well, and I actually do that in the code. Number 3, the Lambda function also sends values to, the Lambda function 2 does something a little different. In function 2, this same stream actually invokes Lambda function 2 to send the result of those data streams to S3 as a data store. Mind you, these 2 Lambda functions can be invoked concurrently, but they can do very different things. And as a reference point here, you can see that we actually have a Lambda reference architecture for stream processing that you can look over and view for more details about this flow. Continuing with the common architecture for Lambda, there also is a common architecture for data processing when we're talking specifically about storage and analysis. And I think this is a very great use case because it's typical in using Lambda. So this use case uses Lambda to fan out to other services, such as storage, database, and BI analytics. So in this common architecture in a data processing for store and analysis, we have Kinesis, this one stream, fanning out to 3 Lambda functions. Those Lambda functions are secured using our IAM policy to say what can and can be done. So the first one has a policy that only allows it to write to S3 bucket, and it can be a specific bucket. The second one has a policy to allow us to write to a specific table in DynamoDB, and the third allows us to talk to Redshift. If you look at it, the steps here, I grant Lambda permissions with an execution role based upon where I'm sending the information. The Kinesis stream continuously captures that data, and then I'm fanning out Lambda with these 3 functions to process this data in multiple ways. Think about this as a directed acyclic graph processing, because this is also available using Kinesis and Lambda. The functions emit results and put the results in the stream, and then you can actually process that for, again, graph processing. Now we've gotten to the point where we're going to talk about our demo. Let me explain our demo before we get into the demo. What our demo will do is it will actually pull social media data from Twitter. We're going to use the Twitter streaming API. And once we do that, we are actually going to take that data from Twitter streaming API and send it through to Kinesis. Kinesis is going to capture those streams of data coming across. It's then going to have Lambda invoke once it sees that records are available in Kinesis. And then Lambda will look at that data, pull out the data points that it wants, and then sends that data to DynamoDB. So let's show this in action. I'm going to share my screen now. All right, you see here I have a typical bash shell. And in this bash shell, I am going to run a function called tweet listen that I've created as a part of a website that dynamically takes the streaming data for Twitter, processes it through using Lambda and Kinesis to DynamoDB, and then my website actually then takes that data from Dynamo and shows it on the screen. The part that we'll show today, since we're focused on the streaming data processing Kinesis and Lambda, is this function running, sending the data to Kinesis, and then Lambda function picking it up and writing it to DynamoDB. So the name of my function here is called tweet listen. So I'm going to go ahead. I'm using Node.js to write this and running this in a node using the node service. So you'll see this waiting for tweets. And while it's waiting for tweets, I'll actually show you what this function does in the code. So if you look at this code here, I have first a config file. We want to be secure here. That actually grabs my data points from Twitter, because I don't want to obviously have my code storing consumer keys and consumer secrets. That would be very bad. So I have a reference to that config service. I have a reference to Twitter so I can access the streaming API, and obviously I have a reference to the SDK. I have credentials that I'm sending from AWS. Note here what I can do, and I actually is a good reference point for you guys to know. Instead of actually sending an access key and a secret key as credentials, I actually can generate credentials from Amazon Cognito, so AWS Cognito. And then all I would have to do here is just send an identity pool. A very safe way to get credentials in AWS, because Cognito negotiates the tokens for me, so I never have to store a password. Once I'm authenticated with that token, and I can use Cognito to not only authenticate me using AWS credentials, but I can get that token from doing an authentication with Facebook or Google and other social media services or other authentication methods. It passes a token Cognito, and I can pass that as my credentials to AWS. In the back end, the IAM policy can say what that credentials and that token can access, and I'm off to the races. So think about that as a way to get your credentials in. back to the streaming data service. So you see here the topic that this is polling for is AWS Cloud and serverless. And the parameters I'm passing for Twitter specifically, so I've already authenticated with, I already will authenticate the credentials with AWS. I need those credentials from Twitter for Twitter to function, and that'll be the consumer key, secret, token key, and token secret. You can get that by creating an application at dev.twitter.com and developer.twitter.com and starting an application. It'll give you these appropriate credentials. Again, I still don't want to give those to the world, so that's where you see me using that config file, and I'm pulling that data out of that config file service that I'm using. So once I do that, I'm just writing some things that you can see here on the screen when we go back to our node screen. I'm writing the topic that's being used. I'm writing the stream name, and then I'm writing where it tells you that I'm waiting for tweets, and you saw that come across when you saw the screen running. Once those tweets come in, I have what we call a callback, and this is based upon the Twitter API that allows me to stream on the data. I get those tweets that come across, and then I actually create and filter those tweets based upon the data I want. So I want the profile image of the user. I want their location if it actually exists, if they stored it. I actually want the tweet ID, the actual tweet, when the tweet was created, so the time, any hashtags that they use, and the picture of the person gets stored here. So you see I'm creating a JSON document here called trimmed tweet. Wow, that's a tongue twister. And then I'm writing that trimmed tweet out to the console. If there is a place or a country, I'm grabbing that as well. And I'm taking all of those params. So I'm taking that trimmed tweet and making sure it is a string, a JSON-based string. I'm getting a partition key. So for Kinesis, you pass a partition key to Kinesis, and that helps it partition the data between shards. Here, because I'm not actually sorting the data by partitions, I'm just giving this a random value to do. And then the stream name that I actually want this information to go to. Here's my put record. We talk about the puts being real time. Here's my put record. So I'm doing a Kinesis put record. I'm passing those parameters, and then I have a callback here just in case an error occurred. If not, you'll see something that says after Kinesis. So let's go back to our bash shell. You see that it's been busy over here while I've been talking. I'll scroll up just so you can see. So again, you see that just as I promised, I wrote out to the console that it was starting to tweets, to stream for tweets. And you see these tweets are coming across. I see that there is someone got congratulated for serverless and chatbots. Remember the topics that I'm searching for, and you see that at the top are AWS Cloud or serverless. You'll see there that someone talked about something with serverless and microservices at the DevOps Summit. And just scrolling down, you see tweets are coming across. So our tweet engine is actually running as we thought. Now, I'm going to go ahead and leave this running, and let's go to the browser now, because I actually want to look at what's going on in the console with Lambda. So here is the Lambda function that I'm using to process these tweets. So the first thing you'll see is that I am declaring all of my variables that I'll use throughout this Lambda function prior to the Lambda invocation function. And then what you'll see here is that the event, that's where the streaming data comes in, is there. The context of how it came in, so it was retrieved from Kinesis, you know, what was the stream name, is the context of how the call was made. And there's a new function for Lambda called a callback. If you've used Lambda previously, you're probably used to seeing context.success or context.fail. To keep with the same type of flow that typical Java functions use with callbacks, we've created a callback function here that gets passed upon invocation that you can use to say if it failed, you pass the error and the error stack for the message. If it did not fail, you pass null as the error and you pass the data back to the calling function. So here I have my event coming in, and remember the event comes in as a batch of records in Base64. So you see that what I'm doing now is taking that Base64 record, I'm stringifying it, not for any purpose that you need to manipulate it, but just so I can write that out to my CloudWatch log. Remember I talked about that this Lambda function was actually going to write to DynamoDB and also write certain data points to my CloudWatch log. And so here I'm actually doing a console log because I want that stringified Base64 records so I can view what actually came in, purely came in, from Kinesis to Lambda in that log. And then I'm taking that Base64 record, so that data comes across in that record as kinesis.data, so that's how I get to the information. It's in Base64 as I noted, and I want to convert that buffer to a string, and I want that to be an ASCII string so I can read it. So creating a new buffer, taking that new buffer, having that loaded with the Kinesis data, noting that it's in Base64, and then I'm converting that to a screen of type ASCII. I'm then also writing that decoded payload or that decoded data, the tweets that are coming across, to CloudWatch using a console.log. That's simple to write to CloudWatch here. Now, what's the next thing you see me do is I'm using a regex function here because sometimes when data comes across the different streaming agents, there are different symbols and other types of things in ASCII that you can't see with the naked eye, but they're there. And that could really screw up my parsing of the data. So what I want to do is, if there are any unseen symbols or ASCII data or text or things of that nature that I can't see, but they're in there, I'm taking this regex function and wiping all those out so I can have a clean parsing from the JSON. And then I try to do best practices here, a try catch just in case I have a parse error. And so I'm parsing that data from JSON. If there's an error, I'm going to write the error to a log so I can use that for debugging later just in case I didn't catch any of the other gotchas when I'm parsing. Actually, there should be something noted here. That's how I caught that I was getting different ASCII, unseen ASCII symbols to in my JSON parse because of this try catch, which enabled me to actually put that regex function in. So again, great to do these things to help you debug. Now once I parse that data, you see that I'm getting the timestamp. I'm pulling out the Twitter ID to string because I'm actually going to store that ID as a string versus a number, which it comes across as a number. And then I'm actually going to formulate a put request. And in formulating that put request, what I'm going to do is store that in an array. Now you'll see this information commented out here, and that actually left that in so I can make a good data point. When I first created this, not realizing how much data I really would come through the pipe of the streaming data, I was doing individual puts to Dynamo. And what do you think happened? My database had a bunch of hot writes really quickly. Not a great thing. So instead of doing that, what's a better way to put this loads of data that's coming across is to leverage a DynamoDB feature called batch item write. And to do that, I am actually taking this data. You have to have a put request and an item, and then I can take that data. So these things right here are required. But the data that I want to put in there, I include into that item node. And once I have that, I actually push this into an array called data items batch push. And I want to make sure, and you see a counter here for me, I want to make sure I'm doing this using the best practices of that function. So I'm tracking the data records that are being put in that array with a counter and writing that out to CloudWatch again for debugging. Now, you see that I have, once I did that, I'm actually creating another JSON holder. I'm inserting into that JSON holder the DVD table, that's the table, that Dynamo table this will write to, and I'm then adding that array into that. And then I'm taking all of that data and writing it to CloudWatch because I want to see the items came across, making sure my parameters were formatted correctly, again another debugging tactic, and then I'm actually writing those data. Now you see the initial thing I commented out, this is when I was doing those individual puts to the Amazon DynamoDB that was causing the hot writes, which was a no-no. We don't want to do that. And so this function db items write is my own custom function to batch write to it. It is here. So I have a function that's outside of my evoke function here, and it's db items write. So I'm taking in the parameters that I just showed you. I'm saying, do I want this to be retried? Because again, you can retry data. We talk about being replayable. I want the context in which it's called in, and I actually want to leverage that custom Lambda callback that I talked about. So I pass that actually into my function as well. This is a call to the batch write. So I'm using DynamoDB client for JavaScript batch write. I send in those request items. So request colon items, that's how you pass in the request. Here's my item data. I have my callback for error as well as data. If there's an error, I'm writing that to CloudWatch. If not, I am processing that. So you probably see something called unprocessed items. This is a great way to Dynamo writes a batch. If any of those batches based upon the batch write limits are not fulfilled, you might have some unprocessed items, left in your data. So if your object returns with a key of data and has data unprocessed, so that's greater than 0, there are a few that still wait in the queue that I want to retry. You then want to use an exponential back off and then retry those. So that's the next two things you see. All of this I'm talking about is clearly documented in the DynamoDB writes. So no fear, you can read about this if you want to use batch write as well. And then if I have finished processing data, because I set a timeout, I retry them, and then it runs again. Once I finish data, I get a success, completed successfully. So let's go back quickly to my node, and you see it is still plugging along. I'm still getting data coming across. So going back then to here, before I show you the log in the DynamoDB table, let's head over to Kinesis just so you can see what I did to create this Kinesis stream. And I promised you it was easy, so let's see how easy it truly is. Now here's a Kinesis console. Again, as I told you, you have 3 options to go into. I am going into streams. You see I have other streams that I have active here. The one that we're looking at is my Dev Day 2016 stream. And here, immediately when you go into the stream once you create it, it gives you the ability to look at the monitoring. So what's the write throughput, bytes per second? See my write throughput is here. What's the incoming records? What's the bytes per second? My put latency in milliseconds. So you see this being run and the put latency here. I see the put records latency here as well. So based upon dates. I see the get latency. I also see how many get requests were made. So how many times Lambda made a get request, because that's the thing that's pulling right now. This can be, you can see this is the get request spike if you have multiple things pulling on it. That spike doesn't affect the process. It just gives you data from monitoring. And then you can see the count of how many put records was actually made. All right, so that's the monitoring Kinesis. When I'm creating Kinesis, you see that it has an open shards. I can increase this and reshard. So if you look here and click that link, it actually shows you how to reshard an open stream for Kinesis. You see, when I created Kinesis, I created it with 5 shards. Now, as promised, I would show you how easy it was to create one. I'll just create one that we can delete really quickly. All I have to do here is create a stream name, so test stream, and then determine a number of shards. The number of shards, there's a best practice and a formula to do that. I'll talk about that in the best practices. But here, just for test, I'll create 1 shard here. It'll create, and then you'll see it's creating my shard, my Kinesis stream with a shard. Literally, that's all I have to do to get that stream created. So again, I did not make a fib or tell a fib there when I said it was really, really easy to create a Lambda stream. Kinesis stream. So I've showed you Kinesis, I've showed you Lambda. Let's actually go and look at the database table that it's getting written to. So if I go to my tables, you see obviously I have a lot of tables here. I specifically want the table that's pulling my stream. All right, so this is the data stream I have. My keys here for this NoSQL DynamoDB, if you're not aware, is a NoSQL database. So I create some partition keys. I'm using the Twitter ID and the Twitter time. So if I look at the items being written, you'll see that those items are indeed starting to become and being written from it. And right now, I have approximately 177 records that have been written to it with the Twitter time and things of that nature. So you can see all of these records coming across, this being run, the Twitter time of when they wrote it being done. So again, this Twitter function is writing to this appropriately and giving me the data coming across. All right, let's go back to my bash shell. And this has been running for quite some time. You see it's still running, so again, these are valid. I'm going to go ahead and stop that stream. Now, again, as this stream runs and as it processes, you can actually see that data coming across. And so you can really validate that, again, this data is working. The last thing I'll show you in this demo is CloudWatch. So I promised that I would show you CloudWatch, and that the fact that the data that I am running is actually writing that custom data to the CloudWatch service, or the CloudWatch monitoring, so you can do debugging. So let's go back over to services. Let's click CloudWatch. All right. So you see, here's CloudWatch. I have various things running. I have different alarms to show that, you know, what's happening here and there with it. Now, I specifically want to look at the logs for that Kinesis data. All right. So you see that I have a myriad of different Lambda functions running, but the one I'm most interested in is my dev day stream processor. You can see that the last event time, which is today, because that's, again, this is the date time, not the Twitter time that the tweet was written. This is actually the event time. You can see the last time this was run was today. And what's great about that is I can see when the data errored out because maybe I couldn't read some of the data in. I can see where it's successful, and it's going to scroll down and give me all of this. Now, what I promised I would show you, I could be scrolling for a long time given that we've been running this for a while. Let me show you something here about how I'm writing the data. All right, so here is let me go all the way to the top. It's still, like I said, we ran this for quite some time, so I have a lot of data here. But let's just take this one because it's the closest one I can get to. All right, so I'm going to drop this down. You see that it has Base64 Records. And this is actually when I wrote out the Base64 record of how the data came across. Remember I said that that data is sent to the event in Base64. I want to actually write it out in its purity, what was actually written to the database. So you see here, here's the partition key that I generated. Here's a sequence key. So once Kinesis processes it, creates a sequence key. Here's the actual data in the Base64 that I converted. The approximate arrival time that it got into Kinesis. The shard ID of what it used for a shard, the invoke identity, so the IAM role that's being used to invoke this, and then the event source, which is Kinesis, which is the dev stream. So this is, as I promised, I wrote this out to console. Another thing you'll see that I talked about when I wrote this out, when I did this, was I actually talked about the fact that I decoded the Base64 records that are coming across. So I'm also doing this through a loop. So you see here that as it goes through the loop, I'm actually decoding the data that's coming across. Here's the Twitter ID, here's the username, here's the text, and the information that comes across. And then the last thing I'll show you here is I also wrote out the put data that was associated with the stream to the database call. So I can actually see what was put there, and if I had any issues, I can then correct it by looking at it. Now in my database, because I'm using Twitter ID and Twitter time, if the stream pulls across a retweet that has very similar data of database and time, I don't store that again. So it'll give me a validation error, but it'll process the other records. So you see here, this is the data that's coming across to the DynamoDB. This is my put request I created. So you see that, all of these tweets are being stored. Again, this was retweeted twice, so one of those will fail because it's not going to send it a bunch of times based upon how I set up my data. And here's the data going across. All right, so let's go to one more thing and then we'll go back to the presentation. So what I want to do now is, we talked about looking at Lambda and Kinesis as an event source, right? There was an event source with Lambda and Kinesis. So let's look at how you set up Kinesis as an event source for Lambda. So going back to my dev stream processor, I have some configuration here. So you see that I need Node.js 4.3, my roles, etc. This is the one we most are interested in. This is the trigger of when Lambda would run, and it's going to run based upon Kinesis dev day stream. So this is showing Kinesis as an event source for Lambda. An event source is what triggers Lambda to function. So you see that the dev day stream that I showed you when we were in Kinesis, what happened? And the last result was I had the last result of it. So the problem I had was a function call failed, and that last result was because those records were duplicated. I got a validation error. That's how I set up my DynamoDB table. I don't want retweets of the same tweet coming across multiple times. So the last function call, the one I actually showed you with Carlos being retweeted several times, only one of those succeeded and the rest of them failed. So it'll tell me the last result of that function. And we saw that actually the other data points were actually being written to the table. So I know that my function is working correctly, but it'll give me the last result, which was, again, one of the retweets of that being not stored in Dynamo, because I did not want the retweets there. So let's go back to the presentation. Great. So now you saw this real-time architecture in action. Let's talk about some of the best practices and tips when you're creating or recreating such an architecture. First, let's talk about the best practices of setting up a Kinesis stream. I did promise that I would talk about how to best looking at shards and a number of shards. The first thing is, streams are made up of shards. So I explained kind of what a shard was. Here's some data points to know about shards. Each shard ingests data up to 1 meg per second, and each shard emits data up to 2 megs per second. You should always determine initial shard size based upon your data that you plan to come in. Now, if you notice when we were in the console with Kinesis, you saw an option that said, help me decide how many shards I need in the console. You can then therefore give it the type of data you have coming across, the average size of the data that's coming across, and then it will determine how many shards you need. So how much data is coming across, with the bandwidth or the speed of the data coming across, and how much you might write it out, some other things, and it'll determine using that algorithm for you. Now, if you're using the KCL or you want to write these puts or dynamically create your stream before you make a put using either the KCL or the SDKs, you can use your own formula. Even in the console, you can just do this formula yourself if you want to determine the number of shards. And the formula for a number of shards is the max of the incoming writes, the bandwidth in kilobytes, divided by 1,000, and then the outgoing read bandwidth divided by 2,000. That's a simple formula to determine the number of shards yourself. So you can use one of those two things to determine that. The thing to know as a best practice is all data is stored for 24 hours. So if you need to replay data either for analysis or debugging or to track certain patterns of the data that happened, you can replay that data within a 24-hour window. Remember, you can also set up an alarm to let you know that within that 24 hours, your data is getting close to expire. But again, the replay data, the default of that data being stored is 24 hours. Another thing that you should look at that's a good best practice is you as the producer. I showed you my code in Visual Studio. My code was creating a partition key. When you're writing to Kinesis, you have to supply a partition key. Now, here's the trick. Being that I am supplying that partition key, I can use that to distribute the puts across my shards. So if I want to distribute puts that are relevant to a certain topic, or let's say I want to sort against my 5 shards, I want to say all the tweets that come across that have AWS Cloud tag goes to this tweet. I could create a partition key for that. All the ones that should go to serverless, I could create a partition key for that. And then I could create another one, etc., etc. It will be used to distribute those puts across the shards in Kinesis. So if you want to determine a customer, you as a customer, determine put across Kinesis, you can do so with that. A unique sequence number is returned to the producer upon a successful put call. You saw that sequence number that was generated from Kinesis that went to Lambda. And then you should make sure your partition key distribution is even to optimize parallel throughput. So as you're building the key, make sure that your key is even. So if you're going to create keys, they should be in things of even numbers. So if I'm going to do 2 keys, 4 keys, 6, etc. But whatever you do, make sure your key distribution will cause an even parallel throughput as you create those. So however I want to divide it, so instead of doing maybe 3 across AWS, serverless, and a combination of both, maybe I should do tags that are AWS Cloud, serverless, the combination of both in the tags, and one with no tags, and just that reference in the topic. Another best practice you'll see is creating Lambda functions. So make sure you write your Lambda functions in a stateless style. I mentioned that earlier, but just make sure you do so. And then instantiate your AWS clients and database outside the scope of the handler. So you saw when I showed you my function, my reference to the SDK, my reference to the database, my variables were outside the scope of the function, of the handler, so the function of Lambda function, so I could take advantage of connection reuse. You can look at how Lambda works and how it uses the connection reuse with the containers that it reuses in the Lambda developer guide. Another best practice in using Lambda, memory. So most people, when they see in the creation of a Lambda function, when you first create Lambda, you'll see 2 options. There's a memory and there's a timeout. What you should know that is the CPU and the disk that gets allocated to your container that houses or creates your Lambda function, creates this instance, is proportional to the memory configured. So here in this example, it says 128. In my Lambda function, I use 512. You can use a minimum of 128 and go up to a gig of memory. But again, there are 2 things to know about memory. So now that you know that it equates to CPU and disk, note that increasing memory makes your code execute faster, and this is if it's CPU bound, and increasing the memory allows for larger records to be processed, so larger record sizes to be processed with your Lambda function. Increasing timeout allows for longer running functions, but more weight in a case of errors, okay? And then for Kinesis specifically, this combination, Lambda will retry if there is an error, if it didn't get the data processed, etc., until the data expires. Remember, that's the default of 24 hours. So I'm going to repeat that again. That's because it's really important. I know I get a lot of questions about that. For Kinesis, as an event source to Lambda, Lambda will retry until the data expires. So if it didn't successfully process that data, it will retry within the default 24 hours. And then remember that your execution role defined for Lambda must have permission to access the stream. So what we find here is some people find errors. It's because you didn't issue the correct execution role that allows for access to Kinesis. Another best practice when configuring Lambda with Kinesis as an event source is the batch size. I promised earlier I would talk about it, and here we go. The max number of records that Lambda will send to one invocation is the batch size. This is not equivalent to the effective batch size. So Lambda is polling Kinesis every 250 milliseconds, and it's grabbing batches. So the effective batch size is related to the polling of every 250 milliseconds. So the minimum amount of records that it will get is the records available plus the batch size that you've allocated plus the 6 meg data memory. The 6 meg data allocation limit. So increasing the batch size allows for fewer Lambda invocations, but more data processed per function. So you see a little snapshot I put down here of it, where in this demo Kinesis stream, the batch size is set to 100, and the starting position is trim horizon. So what does that mean? When I'm configuring Lambda as an event source, the starting position then is important. If I set it to trim horizon, that means it's going to read from the start of the stream. That means all of the data, just like I have mine set for Twitter. I could change that, however, and create another stream that just does latest, which means it's going to do the most recent data first. So a last in, first out model. That's really important depending on how you want to read your data. Another best practice, when you attach a Lambda function to a Kinesis stream, you see my great graph here, remember that Kinesis and Lambda functions based upon shards. So based upon the shards, the Lambda function executes each function per shard. So one Lambda function concurrently invoked per, keyword there, per Kinesis shard. Increasing the number of shards with even distribution, keyword even distribution, allows for increased concurrency. Lambda will block on ordered processing for each individual shard, not across shards, but each individual shard. And the batch size that you determine will impact the duration. Because remember, we said the larger batch size, the more data to be processed, the more data to process possibly will in fact impact the length of the Lambda function to process the more records. Here's some tuning best practices you should know. That the maximal theoretical throughput is based upon this formula. Number of shards times 2 meg divided by the typical Lambda function duration. How can you get this? Remember in the console, when you're writing out the CloudWatch, some of the data that gets written even without you doing a console log is the function duration of your function. So you can use that information and determine what's your average function duration. Therefore, having the effective theoretical throughput being number of shards, batch size, divided by the Lambda function duration. So a little different there. Note, if the push ingestion rate is behind the theoretical throughput, your processing is at risk of falling behind, which means your data will be queued. Remember, it does retries, but again, it will process the retries first before it processes the new data. So you should be mindful that your ingestion rate is not greater than your theoretical input. If you remember, it is going to retry, we talked about, till the record is expired. That's 24 hours default. You always need to retry with exponential backoff. You saw me implement that in the code. And again, your effective theoretical throughput changes based upon the number of retries. So that formula changes where it adds the function duration times the retries. These throttles and errors impacts duration and it directly impacts throughput. So again, you want to make sure that you're allocating your throughput accordingly and not let that ingestion behind. Monitoring, therefore, Kinesis streams with CloudWatch metrics allows you to do this. You can look at the get records. So what's the effective throughput of your get records, byte, latency of records. We saw a little bit of the monitoring in the Kinesis stream dashboard, but for more granularity, you see the CloudWatch metrics. It also shows the put records, so the byte, latency records, etc. Here's the one that is essential for tuning. It shows the iteration age in milliseconds. How old was your last processed records? If it's really high, that means processing falling behind. You need to tune accordingly. If it's close to 24 hours, that means your records are close to being dropped. So you need to tune appropriately as well. Monitoring Lambda, we actually showed this in the demo. But again, you saw I can look at the invocation count in the dashboard. I can look at duration. I can look at the errors. I can see if Lambda is throttling because of the way I'm calling it. I can also debug in the CloudWatch logs, and we showed this in detail when I showed the writes I was making with writing custom events to the logs. You can also do searches through the logs and look at the memory being consumed. One of the key things in looking at Lambda and Kinesis is, and we talked about this in the flow, but just mindful, this is a best practice, Create different Lambda functions per task. You saw that in the example I showed earlier in the workflow, we had one that was writing the DynamoDB in CloudWatch, another one that's writing the S3. In this example, one Lambda function only writes a CloudWatch for debugging. The other one is pushing information to SNS for emailing or push notifications. Make sure your stream, again, it can reuse the same stream, but if you have different tasks, that means it should be different Lambda functions. And here we are to our final slide before we take questions. To get started with this data processing with AWS, here's some next steps for you. Go out and create your first Kinesis stream and play with it. Configure hundreds of thousands of data producers to put data into this Amazon Kinesis stream. Example, data from the social media feeds that you saw me do today. Create and test your first Lambda functions. We have blueprints to help you get started. We have the developer guides. Use any third-party libraries and even native ones. Remember, as you play, the first million requests each month. So each month you get 1 million requests for free. They're on us. Read the developer guide. Look at the AWS Lambda and Kinesis tutorial. Leverage the resources that are on GitHub at AWS Labs. There are some links I put here. So the developer guide is the first one. The architecture specifically for stream processing is the second. It's on GitHub with a Python example. And then there's also an example of streaming data to Firehose with a CloudWatch, or sorry, a CloudFormation template that's available for you to try it out. So leverage those links that I've provided to get you started. Okay, I see we have some excellent questions coming across. Let's read a couple of these and get some answers going. David Vance asks does Lambda participate in a Microsoft transaction? For example, if a Lambda is successfully submitted and then a severe error occurs in the program that submitted the Lambda, does Lambda still process or is it rolled back? And the answer to that, or stated it quite well, but I'll read it out loud. Lambda executes independently. Lambda will not be rolled back in the case you described, but please note that we showed you how to debug. Lambda will show the error, and you could debug using the CloudWatch logs as accordingly. So no rollback, but again, because it works independently. All right, so let's see some more questions here. Will Lambda and Kinesis be made available for HIPAA compliant systems in the future? And if so, when? Well, and Orr stated this quite eloquently, but I will repeat it as well out loud. We typically don't share time frames or timelines for our releases, but your request, Charles Steely's request, was added to for adding HIPAA to our roadmap, and we really appreciate you asking for this feature. But again, it seems to be a common one that's asked, and it definitely is. Your request is definitely being added as a +1 to the roadmap. Okay, so let's see what other questions there were asked. Is there a time frame for Ruby or PowerShell to be added for supported languages in Lambda? So Vishal answered this. He's from actually the Lambda product group, but I'll read this out loud. We don't share timelines, as you know, but again, requests for other languages is something that's really common. It's been added to the roadmap. Thanks for your feature ask. So again, that's something that's being looked at. Please keep requesting new features. We do actually pay attention to those, and again, add those as something that we review for what's the next steps and for features. Samir asks, when I say Java is supported, do you mean JVM compatible classes? Example, if for use of Scala instead of Java. And Vishal answered this by providing there is a reference for Lambda in Scala. So you can look at the blogs for the compute blogs. We actually have a blog post in writing AWS Lambda functions in Scala. So again, we have that available for you if you are a Scala person. There is, let's see, of course we're going to give you guys the slides. We have someone requesting .NET support for it. There was a question about, I think was great, from Prashant. Let me read that one out loud. Node.js is single-threaded. How will Lambda support multi-threading if used with Node.js? and or Noded, which is an excellent answer here. Node.js supports an async model. This is the common model for Node.js for those of you guys who are familiar with Node's single-threaded async processing, but he said it here. Node.js supports an async model via its event loop mechanism, which utilizes multi-threading. To learn more, we actually have this identified in the developer guide, that the link that's in the slides. So if you look in the developer guide under programming model, that answer is available for you. There's also a great discussion on this. I'll add to this, a great discussion on this on Stack Overflow about how Node.js uses parallelism versus multi-threading. And I think you should also check that out because, again, since we leverage the event loop mechanism of Node, this will be a great reference prior to reading about how Lambda uses the program model in this. And the last question I'll take today comes from Vibor Jaswal, and it says, what if the Kinesis message processing crosses 5-minute limit of the Lambda function? Will it be re-invoked? The scope of this question is limited to this presentation scenario. And of course, and or answer this as well, but I'll say it out loud. Hi, yes, the function will be re-invoked as I was describing in the presentation. All right, those are just some of the questions that we answered here. If you have more, feel free to tweet me or go leverage our Lambda forums. We actually definitely monitor those forums and can answer any questions either in our Kinesis forum or our Lambda forum about this architecture. We really appreciate you guys joining today.
All right, thank you, Tara, for your presentation. And ladies and gentlemen, thank you so much for joining us. This concludes today's presentation.